Hello everyone, welcome to a new video, new lecture. Today we're going to discuss machine learning models for time series. So before you continue, it is important that you know how trees and random forests work. So if you haven't watched the previous video, so you should stop and please watch the basics on how they work. All right. So there are some challenges when we're trying to use machine learning algorithms to solve or to make a forecast on a time series. Pretty much because there are some assumptions that are typically, are part of the machine learning models. So when I refer to machine learning models, I'm talking about trees, random forests, even XGBoost. So these classic models, they assume that the observations are independent and identically distributed. But in the case of time series, that's not the case because there can be some structures when the future values will depend of the previous value because there is a sequence, right? And actually we have used that structure to make predictions using Box Jenkins, even exponential smoothing. All right. So that means that when we're gonna split our data in training and test, we gotta be careful, right? Because again, typically for the classic machine learning applications in regression and classification, that's not an issue because there is no a sequence. In your table on your data, you have y and you have some x variables, right? But it does not matter if you change the order of the rows. However, for the time series, that's critical. So when we do the split, we need to keep consistency. We need to ensure that we have consecutive observations. Now, uh, these classic algorithms they don't naturally model time series. Therefore, we need to perform some feature engineering. So this is the bridge. Now, what is feature engineering? Remember that we apply feature engineering when we add new variables into our data. So here in time series, originally we used to have the Y, the time series, or Z, how you want to call it. But feature engineering refers to, okay, let's create here some features, some variables that will be used to find a model to predict our Y. Now, in this feature engineering step, there are different ideas. We can create like features, we can create some statistics like moving average. We can use information about the calendar, some categorical variables such as the day of the week, if this is holy or not. That information can help you to make the prediction. So let me expand that a little bit more because feature engineering is critical for the tree-based model. So you cannot continue one unless you have completed this step because this is how you provide that information to the algorithm. Otherwise, it won't be. You don't have you don't have a matrix with predictors. So we need these additional variables. Okay. So as I was saying, you need lag futures. So what are those? So originally you have your time series. So imagine that you have some values here like 100, 110, 120, right? So if I add one more variable here, which is like lag one, I can call it lag one. So lag one can be like the previous value. So for example, for this observation, for the second one is the previous one. So it's 100. And for the third variable, for the third observation, sorry, you will use the previous value, 110. So this is lag one. But you can create more variables here, like x2, x3. Like here are some ideas. It's up to you, of course, it depends on the context. But so you can keep adding more lags here, x2, x3. That refers to like the observation that is before that value, like how many periods before. So if it's 3, so this is like and days, so 7 days before, like last week, right? So that's the idea of the lag features. So they are very useful, especially for seasonalities. They are important. Now we can also add metrics, and that's the rowing aggregates. So for example, here we're suggesting to have a moving average of the last 7 days for information that is kind of new, or you can have like a bigger window, let's say 30 days. So it's going to capture more like the pattern, and like it's more stable. So you can provide that information and not just mean values. You can also add information about standard deviation, variance, in order to capture volatility, right? We can, like work with the range, with minimum and maximum values. We can add that information as external variables. In terms of a calendar, as I just mentioned before, it can be important in some cases to add like the hour of the day, day of the week of the year, if it's a weekend or not, if it's holiday. And of course, that's one of the nice things about using these tree-based models is that we can add external variables. So not just because all of this so far it's like using the same time series to create these features, but we can also add more information. Let's say that if we're making a forecast about the demand, the sales of a company, so we can include in our analysis where there will be some promotions, price reductions, some relevant information of the context that can have an impact, right, in our time series. So the feature engineering step it's critical. There is something really important here to mention, and it's one of the limitations of these techniques here. If you're using lags, like the previous observation or the last two, the value that is like 2 periods before, so that's a huge limitation because when you want to make a prediction of the future, you can do it only for values or for like for values that are not that far from the last observation. Why? Because if you can predict the next cycle, but it will be difficult to predict like 2, 3 cycles in advance because you don't have those lags, you don't have those values. You only have until the last cycle. There are some ways to solve that. But of course, they affect the performance. So one of them is to use the predictions as a replacement of the lags in order to make future predictions. But you have to keep in mind that these models, their performance is affected if you're trying to predict a value that is like very far in the future. Okay, so in the case of trees, we will be using Python, scikit-learn. Typically, remember that these are the trees. They are very important in machine learning. Not mainly, not because they have like high performance. The main importance of decision trees is the interpretability that they offer. They are easy to follow. They are easy to understand because in the decision tree you can visualize the variables that are important. Typically, those variables will be on top of the tree. The variables that are more important, and you will see at which split or with values that variable is relevant. So that's why we use a lot of decision trees for interpretability. Okay, the algorithm that we'll be using, I mentioned the library, but scikit-learn works with CART, and this one is by far the most algorithm to find to train the trees, right? So it has some strengths, some limitations. I just mentioned the strength. The main strength is the interpretability. Of course, trees can handle non-linearities. That's one of the advantages. The limitation is that the tree in general does not have like the best performance. Typically, they will be outperformed by random forest. So that's why we have here one slide about random forest. So this is an idea. It's not that old. It has like 25, no more than 30 years. Where Breeman, who was the first person that defined, like the random forest algorithm, the idea was to, okay, instead of having a single tree, let's have, like hundreds of trees, thousands of trees. In that way, we capture, like we reduce the variability. So you can see that nowadays, with these websites that where people can bet, like if you have seen Polymarket, for example, they in these websites, people starting to realize that a single expert can be outperformed by several people that are non-experts, right? Of course, there is an incentive for motivation because if they are betting, that's an incentive. They at least they try to get some information before they put a bet, right? So that happens in random forest. It's better to have like weak trees, like weak estimators, instead of a single tree. So that's why typically random forest outperforms trees. That's not a rule that's going to happen always, but in most of the cases that will happen. Okay, let's go and see an example. All right. So let me. Here we have the code. Okay. So in this example, let's go over the data first. So we have a weekly information about CO2 concentration measured at a specific place. Now, instead of working with the weekly data, we aggregate the data and now it's monthly. So it's how it looks. So it has a trend, it has seasonality. You can confirm that when you like visualize independent years. So you see, like the movements pretty much are stable, right? So you have peaks at the same period of the year, and the lowest value also during the same periods, right? So clearly there is a seasonality here. All right. So remember that when we're just using these base tree machine learning models, we need first to add the predictors, right? Because we don't have that now, originally in the time series. So with feature engineering, we are gonna add lags, like previous values. We're gonna add information about the month and some statistics, like the mean value, standard deviation. Okay, so this is how it looks. This is how it looks. For example, lag one. Look at this for this observation, lag one. So the previous one is this y, the original value, right, of the previous value. You can see it here. Lag two is the same idea. So for this one, lag two is the real value of the time series 2 periods before. So this one, right? So now you see that this is why actually this is yt minus 1, yt minus 2, yt minus 3, yt minus 12, and that continues. And then we have the other features. Again, you can keep adding more information depending on the context. So now that we have Y and an X matrix, we perform the split, right? Remember, we're gonna train our models in the training set, and then we're gonna evaluate in the test set. We can do a rolling window or just a basic split. Okay, so let's try to maybe forecast, like using the information in the current state, like the raw data. So here, this is the method for scikit-learn decision tree regressor, random forest regressor. Remember that they have some hyperparameters. So you don't really know the hyperparameters value from the beginning. You need to, if you want to get like the best model, you need to perform some hyperparameter tuning. That means changing these values and evaluate the impact, right? Like if the model is improving or not. So max depth is like the levels that you will have in your trees. And in the case of random forest, we're using here the number of trees, so 500 trees. Okay, so we provide the data. So we have train test, and we get here the performance. For the comparison here of the decision tree and the random forest, we have a seasonal naive. It's very basic. Pretty much the whole idea, since we know that this is there are seasonalities, so if I want to predict the January of the 1970s, I will use the same month, but of the previous year, of the previous cycle, January of 1969. That's how we're finding the naive prediction, the seasonal naive. So very basic, just looking at the previous value that belongs to the same season or the same month, right? Even that basic model, look at the errors, right? It's half of the decision tree and the random forest. So that means that there's something like bad about these models right now, as they are. So pretty much what is affecting is that again, since we only have information of the until the last cycle, then look at the predictions of the tree or the random forest. It looks like a horizontal line. So we need to provide more information, or we need to detrain our series, which is very. There are multiple ways to do it. But one easy way to remove the trend that we have here is just to find the difference between two consecutive observations, something very similar to what we did during box Jenkins. So what we will do here now, so instead of trying to make the forecast with the original time series, let's find a forecast model for the difference. So each observation now is yt minus 1. So it's each observation minus the previous one. So this is the difference. So once we find the difference, it's going to remove the trend. Now the question that you might be asking is, okay, if I do that, how I'm going to make a forecast, right? Because I'm finding now a model is for the difference. It's going to predict the difference, right, of the next period or next periods. So how do we handle that? Well, it's simple. Actually, if you want to make a prediction of the next period, so the forecast, the y hat, if h is equal to 1, is just the last value of the time series plus the difference. So if it's just like the next period, so it's just, okay, the yt minus plus the difference, that was forecasted. If you want to predict like, let's say 5 periods in advance, like h is equal to 5, like the 5 months from now. So the last yt that you have in your data plus the sum of the prediction of the month 1, 2, 3, 4, 5. And that's how you get the real value. Because again, your model is the prediction that the model is giving is for the differences, right? So we use the last value of the time series and then we add those differences in order to get the prediction. So it's not that difficult. Okay, so this is how the difference look. This is the original time series. We see the trend, right? But now, after just visualizing the difference, look at that we have removed the trend, but we still have seasonalities here. We just removed the trend. All right, and now we're going to train, like same models, decision tree regressor, the random forest regressor, but for the difference. Okay. And these models, especially the random forest, look now it's better than the seasonal naive. In the previous one, seasonal naive was outperforming our models, but now the random forest, if you see, both errors are smaller than the seasonal naive. Even the R square reflects that. In the case of the tree, it didn't improve, but in the case of the random forest, it improved. And now it's the best alternative here. Okay, so now we can make our predictions, and it makes a better job, at the predictions instead of using the original model, which was not a good model. Okay, so an important thing here when we have trees or random forests is the future importance. The future importance, because remember that when we create models, typically they have two purposes. When you train a model in machine learning, most of the time you're following two purposes. So the first one for sure is prediction. So you want to predict a future value, right, based on some predictors. And the second one is interpretation. You want to understand which variables are important, are correlated or associated with the response, right? So this is the future importance analysis. So here is lag 12, which makes sense because that means that like the feature or the variable that is the most important variable for the prediction is the observation 12 months ago, right? So if you want to predict January of, let's say, 2027, then the most important variable in this model is the January of 2026, right? So the same month, but of the previous cycle, same season of the previous cycle. And it makes sense because if you remember, the time series here has seasonality, right? So that's why it's suggesting that it's really important. I mean, it's like you see the size of the bar, so the importance is clear. Now, you have to, of course, run the analysis of the residuals, same as previous models. You want them to be independent. You can do some Lejeune box here. Typically, if you have a single tree, you can just plot the tree, like explore the tree, see how it's, like coding the values, which values are important. And you will see like lag 12, it's, it's very important. And it makes sense, right? That's why it's in the future importance, it's on top of the tree. So it's critical in order to make the predictions. All right. So with this, I'm gonna finish the video. So just quickly remind you that it's really important when we're using these tree-based algorithms. Is the first thing that you will need a feature engineering. Sometimes you will need to detrain also the time series. And that's the key in order to get better models. That does not mean that you will get the best model always. This is just one more alternative in your toolkit, because at the end of the day you have like all the options. You can try some exponential smoothing techniques. You can use Box Jenkins, and now you can also use like more like classic machine learning algorithms. So in this video, we explored a tree-based algorithms, but in future videos, we will go over some neural networks in order to do like LSTM, even transformers, right? So I will see you in our next lecture.